Hello and welcome. Today I want to talk about the relationship between non-standard condition Gibbs free energy with the standard Gibbs free energy plus this equation. You see this equation, it took me some years to actually understand why this relationship actually holds true. Now check this thing out. Suppose you have a del G naught value. Let me just talk a bit about what del G naught means. It's called as a standard Gibbs free energy. Okay, let's use a short form for it. Standard Gibbs free energy, del G naught. And what is the standard thing? When the concentration is 1 molar both of reactant and product, and the temperature equals 298 Kelvin or 25 degrees centigrade. Okay, so that's a standard condition in which you have the tabulated value, right? So if you take any non-standard condition where the concentration might not be 1 molar for the reactant and the product, there could be some different values, and maybe at a different temperature, so we'll have a different value for Gibbs free energy. According to me, what I've understood about Gibbs free energy is the total energy for doing useful work or for doing work. If it is negative, that means I have this much of energy. Suppose it's minus x kilojoules. Suppose I have minus x kilojoules. It tells me that this is the amount of energy that is left for me to do work. That's it, right? Now, and that's equated by del H negative T delta S. Okay, now coming back over here. Now, why this relationship holds true? The problem with me to understand this thing was this plus sign over here. Now this was the biggest problem. As it tells you del G value, you might get some del G value over here. Suppose say I get an x kilojoules of energy over here. So it is not necessary that every time you're going to add something over here. It could be a minus, it could be a plus, right? From the standard condition, there could be more energy. In a non-standard condition, there will be a more energy or less energy. So this term that's added over here actually gives you the more or less than the standard condition, right? And one more thing, I also got confused as del G naught to be equilibrium condition. Let me tell you, del G naught doesn't mean equilibrium. Equilibrium is a kind of a position where there is no energy left for doing work. That means del G equals 0, and del G naught is not equal to 0. Okay, so this is a standard condition, right? Now check this thing out. Over here I've got RT natural log Q. This value of del G naught is in joules. Q is just a number, maybe a fraction or a whole number, whatever the value is. So Q is a value. So temperature is over there, and you have got R in joules. If you cancel the R and T units out, what you're left over here is joules. So which is why the R term is there and T is there, so that's, they could be cancelled out, and finally you get everything in joules. Alright, so joules plus or minus joules plus or minus joules and plus or minus joules is a joule, so that will be the value for del G. Okay, so now let's check out. Now suppose if the reaction is taking at the standard condition, then in that case del G has to be equal to del G naught, right? And let's check it out. Del G equals del G naught plus RT natural log of Q. And what is the meaning of Q? Is the reaction quotient, and at this particular position means the time of reaction, where everything is 1 molar. So if you get 1 and 1 over 1, you get a 1, so Q becomes 1 over here, and natural log of 1 is 0. Okay, natural log 1 is 0, so everything multiplied by a 0 gets you a 0, so it actually becomes del G equals del G naught plus a 0, right? And if the condition is something else, if it is a non-standard condition where things are not 1 molar, so you might get a different answer, maybe a positive thing added to del G naught or a negative thing. So how do you get a negative thing? Because the plus doesn't give me a sense that there is a negative thing. The thing to ponder upon over here is the natural log stuff. Now let me tell you, suppose you have a log base 10 1 by 100. So what's the value for this? So you can write it as log base 10 is there, 10 to the power minus 2, and it gives you minus 2 as the answer. Now you see the minus term comes from the log, so the log over here gives you that the term can also be a minus. So that means if you get a minus sign from this thing, okay, if you get a minus sign from this thing, then that tells you the reaction has Gibbs free energy left in it for doing work. That's a negative. And if you have the standard condition to be a minus, and you get a minus from here, minus and a minus added, and you get more of the Gibbs free energy, that means you have got more energy than the standard condition, right? If you give a plus, if you get a plus value over here, so this thing actually means that the reaction will move. It's not equal to K. Maybe K is actually more till it reaches equilibrium. Before it reaches equilibrium, that means here Q is smaller than K. Maybe K is some other value, not 10 to the power of minus 2. Maybe it's some other value. So the reaction will move towards the product side as Q is smaller than K. When Q is smaller than K, you'll have some energy left in it, and it will give you the answer to this question: how much energy have you got when for a non-standard condition, right? So you'll get a minus value over here, right? So, and what if the value is plus Q? That means Q is greater than K. Okay, here if the value is plus, suppose Q becomes 10 to the power of 2, suppose 100, Q becomes 100, that means you require energy to get the equation back into the equilibrium position, okay? Or equilibrium position means that when it becomes equal to K, so the product will become reactants, so you'll be having less energy in it. That means you actually have to dispense energy to carry out the reaction. So suppose in a standard condition you have got a negative value, and in order to reach the equilibrium point you need to add some energy to it so as to reach K, so you will get the difference for the non-standard condition over here, right? So if I think you might have understood what point I was trying to make. Thank you very much.